Hi everyone. So chapter 3 is all about examples of complex functions. So we've studied the complex numbers a little bit, and we've learned a little bit of the basic definitions and properties of complex functions, but we haven't really actually looked at any complex functions yet. Well, at least any holomorphic ones, except for really simple ones like polynomials. And so this chapter is going to give us a bunch of functions that are important in applications, and so that we have sort of more examples to work with through the rest of the semester. So the first really interesting class of complex functions that we're going to look at are called Mobius transformations, or alternatively, sometimes they're called linear fractional transformations, or LFTs, sometimes you'll see. So they're really simple to write down. So a Mobius transformation is a function of the form, it's basically a ratio of two linear functions. So it looks like a linear function, az plus b, divided by another linear function, cz plus d. And now we're going to allow these constants, a, b, c, and d, to be complex numbers. Okay, and these are Mobius transformations. However, there's one restriction. So we also want to enforce the fact that AD minus BC is not equal to 0. Okay, so that seems a little mysterious at first, but we'll see why it's important in just a minute. So first, let's look at this function. So f is defined almost everywhere. We just have to be careful about dividing by 0. So when is this denominator 0? Well, if z was equal to negative d over c, then we get 0 in the denominator. So f is defined everywhere except negative d over c. And so it gives us a function from the complex numbers minus negative d over c. So this notation just means everything except the point, negative d over c. So that's the domain of the function, and then a priori it goes to c. And that's the definition. So the next thing to say, I think, is that f is injective on its domain. Oh, one thing I wanted to add before saying that. So I claim actually that f is holomorphic where it's defined. So note that this function is holomorphic. So it's differentiable everywhere on its domain. Why is that? Well, it's a ratio of two linear functions, right? So we know that the identity function is holomorphic. We know that multiples of the identity, or multiples of holomorphic functions are holomorphic. And then if I add a constant, that's still holomorphic. So this was just from the properties of derivatives in chapter 2. And also we know that if the derivative of two functions are defined at a point, then as long as you're not dividing by 0, the derivative of the ratio is defined, and it satisfies the usual quotient rule. So the derivative of f is defined everywhere except when we're dividing by 0. So everywhere on this domain here. So that's good. So it's a holomorphic function on its domain. And then I want to claim also that it's injective on its domain. So maybe I'll make this a claim. And let's prove it. So we're going to prove it by well, let's just take 2 points. So take 2 points, z1 and z2 in the domain of f. We will show that it's injective, which means that if f of z1 equals f of z2, then z1 equals z2. Okay, so let's assume that f of z1 equals f of z2, and we're going to try to show that z1 is z2. So what is f of z1? Well, it's az1 plus b over cz1 plus d. F of z2 is az2 plus b over cz2 plus d. Okay, and then I'm going to just clear denominators here. And so this is az1 plus b. So if I divide both sides by both denominators, then I get cz2 plus d multiplied by the numerator on the left, and on the right side I get az2 plus b times cz1 plus d. So again, I'm just multiplying both sides by cz1 plus d and by cz2 plus d. So I'm doing that over here too. Right, so this cancels, that cancels, that cancels, that cancels, and I'm left with the expression below. Okay, so the proof now is just a bunch of algebra. So let's just FOIL everything out. So on the left side I get a c z1 z2 plus a d z1 plus b c z2 plus bd, and then here I get a c z1 z2 plus a d z2 plus b c z1 plus bd. Okay, and then we can cancel several things. So that are equal. These cancel. And so what I get is, I'm just going to move everything to the left-hand side. So I'm going to subtract this part from both sides. So I get AD_Z1 plus BC_Z2 plus AD_Z2. Oh, minus, because I'm subtracting that from both sides. Minus BC_Z1 equals 0. That's what that simplifies to. And then I'll just factor things out. So I have an AD times Z1 minus Z2 plus BC times Z2 minus Z1 equals 0. And so if I pull out a minus sign here on this side, this simplifies to AD minus BC times Z1 minus Z2 equals 0. And notice we assume, or maybe I should say, because of our definition of a Mobius transformation, we always have this condition that AD minus BC is non-zero. So by the definition of a Mobius transformation, AD minus BC does not equal 0, which means I can divide out by it. So if I divide both sides by AD minus BC, which I can do because it's not 0, what I get is z1 minus z2 equals 0, which implies that z1 equals z2. Okay, and so that's the proof. Now, the thing to notice here is that this explains why we have this condition. So, oops. If we didn't assume, or let me say it this way. If AD minus BC does equal 0, then working through this, actually everything I did here is an if and only if. So this would imply that f of z1, so this would imply that this was 0, right? Which would mean that this was 0, etc. You work your way up, and it would imply that f of z1 equals f of z2. Which would mean f is a constant function. Constant functions aren't very interesting, and that's why we exclude that case. So that's why we always assume that AD minus BC does not equal 0. Okay, so so these functions are injective, and actually what you might ask is, okay, if it's a constant function, what's its value? Well, its value would have been a over c in any case. So if we had a constant function, this is what its constant would be. But we are assuming that AD minus BC is non-zero, so we don't have a constant function. And actually, you can check by kind of a similar argument that this means that we're never going to obtain the value of a over c. So in fact, assuming this condition, which we always do, then f of z never equals a over c. And in fact, more is true. It actually hits every point except a over c. So proposition is the Mobius transformation which we've been looking at is a bijection from its domain, which is every point except negative d over c, so c minus complex numbers minus d over c, to every point except a over c. Okay, so it's injective, which we showed, and it's surjective onto all of the complex numbers except a over c. And so it's a bijection, so you might ask, what is its inverse? So it has an inverse function. So the inverse, f inverse of z is going to go from c minus a over c to c minus negative d over c. And its formula is given as follows: dz minus b over negative cz plus a. Okay, and so what you'll notice, so check that this it's got the same form as f, right? It's a linear function divided by a linear function, and you can check that it satisfies the same property, that this quantity is non-zero. So check by hand on your own that this is a Mobius transformation as well. So what that tells us is that Mobius transformations have inverses, and their inverses are also Mobius transformations. Okay. I think that's all I want to say. So you're probably asking, like, why is this the inverse? How do we know that? Well, that's going to be a homework exercise. So I'll leave that to you all. And I think we'll call it good for today. And next class, we'll go into more interesting properties about these functions.